Hi, in this lecture I'm going to go over energy in simple harmonic motion, usually abbreviated SHM, simple harmonic motion. So what energies are the relevant types here? Because we've got something moving, there is going to be kinetic energy and then a second one, so the two relevant ones. Two relevant energies. There's going to be kinetic energy. And then, of course, energy stored in the compression or extension of the spring, right? So if you imagine a spring and you squish it, you can imagine me putting like a marble on top of it. You let go, the marble's gonna get shot into the distance. There is energy stored in a compressed or stretched spring. We're going to call this the elastic potential energy, or the spring potential energy. Essentially two terms to mean the same thing. Pot and potential energy. Maybe you've met those before, this example in a previous mechanics course. We know what kinetic energy is, half mv squared. That doesn't change, that it just depends on the mass. Now, what is the potential energy? Let's remind ourselves what potential energy is in general. In one sense, it's the energy stored in, or the energy associated with, the configuration or position of a system. Let's write this down. Potential energy is the energy stored or associated with the position, or more generally the configuration of a system. So in our case, in the case of the spring, the position of the mass, right, that determines how squished or stretched the spring is. I can say the configuration of the spring mass system, essentially saying the same thing. Another way to think of potential energy, and that's the more useful one for our mathematical purposes, to actually figure out an expression for it, is that it is the work that could potentially get done by the interaction that can potentially, and I'm phrasing it in that way to make clear where potential in potential energy comes from, work that can potentially get done by the relevant interaction as the system moves between the chosen point, so the point where you want to find the potential energy, and some reference point where the potential energy is defined to be zero. More often than not, we really just care about potential energy differences. So where you define that reference point tends to be not really physically relevant, but it can be mathematically convenient or inconvenient. And yet another way to think of potential energy is not as the work could potentially get done by the interaction, but conversely the work that we have to do to get the system to that point. Right? So this interpretation of potential energy says, look, I'm stretching my spring. When I let go, how much work is the spring going to do before the mass is back in the center? Or I can think of it as, how much work do I have to do on the mass to push it from the center, from the equilibrium point, to the point where I'm trying to talk about, the point where the potential energy is whatever value, that I'm I'm trying to find out what it is. Alright, so I could also say that it's the work I have to do to get the system from the 0 point. The 0 point meaning where the potential energy is defined to be 0. In the case of the spring, that's going to be the equilibrium point. To the chosen point. So the point where I'm trying to find the potential energy. So that's the wordy explanation of what potential energy is. Right? Hopefully that's just a reminder. Now let's apply that to our special case of the spring. So here I've drawn this situation for a spring. I'm going to assume the spring is horizontal, so I don't have to worry about gravity as well. Of course, in terms of energy, I could easily accommodate gravity in a vertical motion by also including the gravitational potential energy. And in class and in the homework, we'll be doing examples that do involve gravity. So here's my spring, and I imagine in this top picture it's at the equilibrium position, so there is no force on it right now, and we can just intuitively see that it's got to be at the lowest potential energy here, because it's neither squished nor stretched. There's no energy stored in the spring. Now let's imagine I'm going to take this mass and I'm going to move it over here to some position x, some arbitrary x value where I imagine that the equilibrium point is x equals 0, and so this is some other value of x. How much work do I have to do to push it from here to here, right? That is how I calculate the potential energy. Alternatively, as I just outlined, I could calculate it by saying, okay, if it starts here and I let go, how much work is the spring force going to do to move it back to here? Either way, you're going to get the same answer. So I'm going to calculate the work I need to do to push the mass from here to here. Okay, now work equals, and I'm going to write this in sort of rough terms, force times distance. Right, of course this is rough because really I should be writing F as a vector dot delta x. Right, but even that is, so the dot product involves the angle, so really I'm just taking the force component in the direction of the displacement. Hopefully you remember that from your mechanics course. But even that is only rough because what force do I take? The force here, 0, the force here, halfway, the force here. Like, what do I do? But here, F keeps changing, so how can I calculate it? Along displacement. Right? The force here is different from the force here, because here the spring is going to be more stretched than here. I've got to push it all the way over here, so at the beginning it's going to be easy, little force is needed to push it. But as I stretch it more, I've got to push harder and harder and harder. How do I accommodate that? So we're going to do, we're going to take tiny steps, find the work for each step, and for each step, of course, it will be different from other steps, because it depends on, is it the first step, is it a later step? Here I'm going to do more work than here, because I've got to push harder when the spring is already stretched. So find work for each step, then add. Okay, so let's do that. Here's the corresponding drawing. I imagine I start here, I want to get all the way to here. I'm looking at one step somewhere along the way. So imagine I'm going to take a tiny step from here to here. Of course, I had to draw it. I had to draw the step sizable enough that we can actually see it. And mathematically, what I'm going to do is I'm going to make those steps infinitesimally small. And now, because essentially I'm not moving very much as I go from here to here, you really have to imagine those are really, really close together, those 2 points. So those boxes should really be overlapping, right? The force at this point here, where the step is occurring, is just k times the x position of that step. So the work done for the step I'm pushing it from here to here, that little step is going to be f times dx, and f is constant for the duration of that step. It's going to be kx dx. Right? It's kx because I just have to push to cancel out the pull of the spring. The spring pulls with a force that's kx to the left. Now, you might think, hold on a minute, but as I go from here to here, the force does change, right? Because the x increases, namely by dx. And here again, I remind you that we're going to make this dx so small that the difference between here and here is essentially negligible. In fact, it is going to be mathematically negligible, 0, in a well-defined way. Right, so the force in this segment here, this segment I imagine to be so short that for all practical purposes, the force within it stays the same. So this is the force, the work done for one step, F dx, and of course my force is in the same direction as the displacement, so you don't have to worry about components of F in the direction of displacements or dot products or anything like that. And then I've got kx dx because F is equal to kx. So now we want to sum up those steps. If I can leave this up here. Now sum up steps. From where do we start? We start where x equals 0, and we go to some final value here. Why don't we call this value x1? Give it some name. x 2x equals x1. When I say sum up the steps, I mean the work done for each step. So I get the total work. It's going to be the sum. Now what do we call a sum of an infinite number of tiny, tiny, infinitesimally small steps? Call the sum like this. Sum starts at x equals 0. The sum ends at x equals 1. Of the work for each step, which mathematically is from x equals 0 to x equals x1, some arbitrary value where I'm trying to find the potential energy, kx dx. That is clearly something I can evaluate. It's going to be x goes to x squared over 2. So I've got 1/2 kx squared evaluated between x equals 0 and x1. So I get, just plugging this in, x1. And 0 gives me nothing. So the total work done to go from 0 to the position x1 is 1/2 kx1. Now I had to call this x1, I couldn't just call it x, because I used the x to sort of count where I am along the way, but and then now of course, right, having figured this out, potential energy at x is given by 1/2 kx squared. Alright. So let's do just a very short numerical example to calculate this, to do a calculation with this. Let's suppose my example is the following. Example, say it takes 0.3 joules of energy, of work, to compress a spring by 0.2 meters by 20 centimeters. Find K, spring constant. Well, I just have to say that the potential energy U, now U is a symbol often used for the potential energy. Maybe I should write this here. In general, not just potential, maybe you've met it in some other physics applications before. U for potential energy. U of, what do I know? I know at 0.2, so U of 0.2 is equal to 1/2 times K times 0.2 meters squared. And that better be equal to 0.3 joules. So I can rearrange that to find K. K is going to be 2 times 0.3 joules divided by 0.2 meters squared. That is 0.6 over 0.04, which makes 15 newtons per meter. And with units, remember joules is giving in Newton times meter. I divide by meter squared. I'm going to get newtons per meter. Okay. That is just a very simple example applying this expression. Now here's a second example. I imagine there's some ball or some object that's going to be rolling down the hill. The hill has a height h, the object has a mass m, and somebody put down here a spring with a spring constant k. We assume we're on Earth or at least some planet. Find the distance by which the spring compresses. How am I going to do that? Well, I'm going to use energy conservation. Every time I have a situation where I have some early point in time, some late point in time, energy conservation is probably going to be helpful. So what energy is energy is conserved? What energy is converted to what? So initially I've got gravitational potential energy, gets turned into kinetic energy gradually, and that gets, when it hits the spring, it's slowed down. The kinetic energy is converted into elastic potential energy. So let me just write this down. Right up here, it's gravitational potential energy, which gets the gravitational potential energy is gradually becoming kinetic energy, and then when the ball hits the spring, it has no more gravitational potential energy, at least assuming this is our reference zero height. So over here we're going to have the kinetic energy gets turned into elastic potential energy. Now, because energy is conserved throughout, right, the energy here, the total energy here is the same as the total energy here, is the same as the total energy here, all I have to do is compare the energy right at the beginning to the energy right at the end. And at the beginning, I have the gravitational potential energy is of course mgh. Kinetic energy is 0, which is starting at rest, as part of our assumption. And because the spring is far away, it's not squished or stretched at all, the elastic potential energy is going to be 0 as well. Now, when we're at the end, right, at the end, of course, it's not the end of the action. And once it's there, you know, other things are going to happen. It's going to push the ball back. Maybe it'll roll back up the hill. But at the end of this rolling down motion, right here, the gravitational potential energy is 0. The kinetic energy is what? Well, if it's all the way compressed, it's not going to compress any further. That means the ball must have been brought to a stop The kinetic energy is 0 there too. And the elastic potential energy, well, it's going to be 1/2 k, and k is assumed known, times the squish squared, let's call that x. And that's the thing we want to solve for. Right, this is the thing we want to find. So let's use energy conservation. So it means mgh plus 0 plus 0 is equal to 0 plus 0 plus 1/2 kx squared. Now why am I writing down all those zeros? Just to make explicit that energy conservation means total energy before and after is the same. Right? I'm not saying gravitational potential equals elastic potential. That's kind of what it's going to end up being. But fundamentally I'm saying the total initial energy is the total final energy. But of course all the zeros, they are just zeros. So I can rearrange that to get x is equal to 2 mgh divided by k. But then x is squared, so I'm going to take the square root. And you can easily double check that indeed, if you plug that in, that equation is true. So it's an example of actually using energy conservation to do a calculation. In this case, it also included a different type of potential energy, namely gravitational potential energy on a planet. But that is something you're probably more familiar with than any other type of potential energy you might have met in the past. Alright. Here is a graphical representation now of the potential energy. So I plotted energy on my vertical axis and just the position on my horizontal axis. Here I imagine that x is 0 in the middle, and positive x means stretch, negative x means it's compressed, just a displacement from the equilibrium point. Although I could have, of course, chosen my coordinate system to point the other way around. Now what you notice right away that you maybe have noticed already just by looking at the algebraic expression, that is that if I compress the spring by a certain distance, the potential energy stored in it is the same as if I had stretched my spring by that same distance. At least ideally. A realistic spring, depending on the type of spring, it will of course not stretch infinitely. Eventually you just have a long piece of metal in your hands. It might not compress very far. For example, the metal of the individual windings, they might touch each other and then it can't squeeze it any further. So realistic springs might sort of cut off somewhere, just based on the fact that they're made from metal, right? Or some kind of material that doesn't go through itself, for example. That the windings have a certain thickness and so on. But let's stick with this idealized case. Let's imagine I take my mass, the end of my spring, and I'm going to move it, and I'm going to squish the spring by a certain distance, say this. Say this is my initial compression. Right, so I've compressed it by this distance. That means my spring has a certain amount of energy, stored in the fact that it's compressed. And now that energy is going to determine the total energy of the system once I let go. Right? So if I plot a line here, that line represents my total energy. Now, you may have met those sorts of energy graphs before in your mechanics course. Again, it depends a little bit on where you took it, who taught you, what their preferred emphasis was, but hopefully you've seen something like that before. So this is the total energy, right? That's just given by the fact that I moved the system here to that point, gave it potential energy, but right as I let go, it doesn't yet have any kinetic energy. And now the total energy, that stays the same, that's why I drew this straight line. So if now the spring moves by a certain distance, say from here to here, right, then this, the missing energy, the missing potential energy, that represents the kinetic energy. Because the total is the same, the potential is this, therefore the missing part is the kinetic. And right at the bottom, of course, this is where it's all kinetic energy. Right at the equilibrium point, no potential energy. Whatever energy I gave it here, it's all going to be kinetic. So this is the point where it has the most speed. Maximum speed. We're going to calculate what that maximum speed is in just a second. So to do that, let's figure out what the total energy is. Well, it's going to be a half times x, so a half times k times x. But if I move it to here and let go, it's going to oscillate between here and the same distance over here. It's never going to go any further, right? Because it can't go further, because it would need more energy than it has. So these are going to be the turning points. So that means this distance here, and put it up here, that's going to be the amplitude. Right, so the total energy is the potential energy at the maximum extension, because there's no kinetic. Therefore, total energy is given by 1/2 k a squared. So this value, if I know the amplitude and I know k, I can find the total energy of the spring. It doesn't mean that it's all potential all the time, right? When I'm here, the potential energy is 1/2 k, whatever that value of x squared. Right, and that value of x here, in the line where I've drawn the green arrow, it's not the amplitude, it's some smaller value. But then I have some missing energy, and that's the kinetic energy. So if I now want to find the maximum speed, I use the fact that 1/2 mv squared, m is of course the mass of that object at the end of the spring, the mass, that's equal to the total energy, since no potential, so this is going to be a max, subscript max, no PE at the equilibrium point, right? So all the energy is kinetic, but I know that the total energy is given by where I started, the potential energy at the end point, because at the end point there is no kinetic. So the potential energy here is equal to the kinetic energy here, 1/2 ka squared. So that implies that the maximum speed is, I can cancel out a half, I'm going to get k over m times a squared, but then I'm going to take the square root. It's going to look like this. Double check that that is indeed true. Now, if you've paid attention in the previous lecture, then you know that the square root of k over m that's come up before, that is just an expression for the angular frequency, or the angular velocity of an oscillating mass on the spring. And so it's another way of writing the maximum speed. Can I check that? Well, we can check it from the kinematics that we know. Check using kinematics. What we derived in the last lecture is that the velocity as a function of time is given by a omega cosine omega t plus whatever our phase constant is. Now, the cosine function, of course, whatever's inside is going to be between -1 and +1, so that indeed means then the maximum magnitude of this is a omega. V max is going to be a omega, just like we had up here. And so that confirms that same result, right? We derived it twice, once using energy, once using the kinematics. That is pretty much all there is to say right now about the energy in simple harmonic motion. The rest is really just applying this insight to a broader range of phenomena and problems. Good luck with that. Let's see you in class.